right, y'all, we are live, I believe. It's that time again. Today is day 5, relearning calculus. My name is the Math Hobbyist, and today we're just going to be working a lot of problems on limits. So yesterday, 2 days ago, we introduced the intuitive definition of a limit, and we worked a couple of problems from Taalman. Yesterday was a fun stream. We didn't work any problems. All we did for an hour-ish was just see many different definitions of a limit according to several different textbooks. We just kept redefining limit again and again, starting with Taalman's intuitive and then epsilon delta formal definition of a limit. And then we saw how other mathematicians actually treat epsilon delta as a result of something simpler. So we defined limits of Cauchy sequences, and then metric spaces, and then topological spaces as well. So go check that out if that sounds interesting. But today we're going to be back to problems. We're going to do problems, I think just from, I wrote down 1.1 and 1.2. I think we will do 1.2, which is the formal definition of a limit problems. I think we'll be doing that tomorrow or in the future. We're mostly at least going to be doing several from 1.1. And then soon, maybe it's tomorrow, hopefully we'll be getting to the definition of the derivative, which really just depends on the definition of a limit. And I'll just be starting to state some of the properties of the derivative. Maybe we'll prove a couple of things, and we'll start to see how they're useful by applying them to some differential equations soon. That'll be another textbook, but today we are still just on limits. So here's the first problem. I have Taalman 112. Construct examples of the following. First, the graph of a function f for which f of 2 does not exist, but the limit as x approaches 2 does exist. Okay, and then we have the graph of a function where both the limit and the value exist, but they don't equal each other, and then a graph of a function for which neither exist. It says try to choose examples that are not in the section. Well, guess what? I haven't even read the section, so maybe maybe I'm reusing the same examples, maybe not. I don't know. Okay, so f of 2 does not exist, but the limit as x approaches 2 does exist. I like to choose the simplest possible answers for everything. So and that's because I'm a programmer, and in programming, please choose the simplest possible example. Make the simplest possible thing every time that you can. Whenever you're building software, please use the simplest implementation you can. So here's the simplest thing I can think of. I suppose we could do y equals 0 instead of y equals 2. That would be even simpler, but then it's a little harder to draw. So I guess I'm contradicting myself a little bit. But anyways, we're going to have a constant value, really any constant value k, if x is not equal to the point 2. And that's it. Yeah. So this is just defined for all x values other than x equals 2. So I don't even need the what's it called? Piecewise function thing. So we have a constant function. We are saying that the domain of this function is the real line except for the value 2. Okay, that's a simple explanation. Y equals k. K could be 2 if we want to keep reusing the number 2, and that's what I drew. Let's move on. Graph of a function for which both exist, but they don't equal each other. Again, the simplest dang thing we can think of. Let's make that, in this case, what I was trying to define a moment ago. I don't know, let's use 1. If x does not equal 2, and maybe it's the number 2 at this point. So this time, the domain of the function f is going to be the entire real line. And our graph, as we were asked, is going to have a hole at x equals 2, and it's defined as another point at x equals 2. The graph of a function for which neither exist. Okay. So maybe we want to create. So when it says the limit doesn't exist, there are a few different ways that a limit may not exist. One is if, say, the function has a vertical asymptote. That's one way. And this could be, so there's one graph. Here's another graph. Basically the same, but not using the absolute value. And then another interesting graph is something like a sinusoidal thing that really just starts, it blows up, it keeps oscillating up and down at x equals 2. So there's another graph. There are 3 different graphs, and this thing is only asking for the graph, so I'm not going to try to come up with an example of a function for that one. But at least for these others, I think I could get one. It looks like it's going to be, for this first one, it's going to be the absolute value of 1 over x minus 2, I think. For this one, f of x, it looks like I drew negative 1 over x minus 2, I think. When x is less than 2, then the value is positive. When x is greater than 2, we have a negative value. And when x tends to infinity, this is going to tend to 0. When it tends to positive infinity or when it tends to negative infinity. So the limit doesn't exist. In this case, the limit as x tends to 2 from the left does not equal the limit as x tends to 2 from the right. From the left, it tends to positive infinity. From the right, it tends to negative infinity. So, whereas in this case, the limit as x tends to 2 of f of x is positive infinity. So I don't know if Taalman means that this exists or not. The limit exists as infinity, but it doesn't exist as a single value. So I don't know. I don't know if what she means by exist in this case. It doesn't matter. And then this one, definitely the limit does not exist at this point. This is, again, at x equals 2. Cool. All right. I feel good about that as a solution for 112. Let's go ahead and cross it off in our nice little table of exercises. We did number 2. Boom. Next we've got, I just wrote down like 25, 26, and a few others. I wrote down at least 3, 25, 26, and 27. So let's take a look at those. Yeah, so again, we're still sketching graphs. In this case, we were given a specific scenario, and we're supposed to sketch some graphs. So maybe let's now solve this one in blue. Why don't we, again, do it below so that we get some nice amount of space. Number 25. All right. Well, the simplest damn thing I can think of here is the constant function. As x goes to negative infinity or positive infinity, yeah, f of x equals 2. Doesn't even depend on x. As x goes to infinity or positive infinity, this function is always 2. That's a simple example. Okay, now this one is like that vertical asymptote that I drew. X going to 2 from the left, x goes to negative infinity from the right, and then at the point 2, f of 2 is defined as 1. So there's a graph. Do we also need to write down a function, like a closed form version of a function for this? It says, sketch the graphs of functions that have the given limits and values in exercises 21 to 30. Yeah, I guess it doesn't matter. Like, this is something like, I don't know if the graph is exactly matching this, but it is what we just found, like -1 over x minus 2. At x equals 2, the denominator is 0. So when x is like a little bit less than 2, then this is going to be a positive number. Like the denominator is going to be positive. Or wait, no. The denominator is going to be negative if x is a little bit less than 2. Think like 1.9 minus 2. So then we have a negative in the numerator and a negative in the denominator. So the value is positive, and we're going up to infinity. If x is greater than 2, then the value is negative. So this is defined for x not equal to 2, and then piecewise we just define it to be 1 at x equals 2. All right, next one. Limit from the left and from the right, both are 2, but f of 3 does not exist. How is this different? Well, okay, again, this is not that interesting. Again, I'm going to create 1, 2, 3, a constant function that is not defined at one point. F of x equals 2, where the domain of f is the real numbers except for the number 3. Here's another notation besides the ones that we had before. I think like the backward slash is one way, or minus. This set minus the 0.3. So that's another way to write it. All right, so we just crossed off a few more, and these were all easy. I don't need to return to them. I'm going to feel good about myself. And I want to clean up this just a little bit before we add on too much technical debt here. 21 through 27. Oh, geez. Okay, I think that this works. Oops. I'm confusing myself. All right, so let's put that there. Let's move these, I don't know, down or something. Let's erase a couple of these. And let's move these in this spot. Let's put 28, 29, 28, 29, 30, dot, dot, dot. And now let's put some of these application problems next. Oops. Dang it. This isn't working the way I wanted it to. Okay. We're getting mastery on Notion, or on Notability here. We're learning. Okay. Cool. So now I've cleaned up our little table a little bit. How's it going? Thanks for the like. Somebody liked the stream. Drop a comment in the chat. Let's hang out. Let's solve some calculus together. Let me know what you think. How's this going? Do you like this idea? All right, so we've solved a few. Now we're going to get to some applications. Yesterday, or 2 days ago, we solved some sort of problem about a warthog population, and now we have a population of squirrels. So it turns out, it looks like calculus can be pretty useful for understanding collections of animals. So far, that is my idea of what this stuff is useful for. We're taming groups of animals, apparently. And I bet that we will get some differential equations about that as well. So I didn't finish writing this. Let's write this one out. There are 4 squirrels currently living in Linda's attic. What happens next? If she does nothing to evict these squirrels, the number of squirrels, the number of squirrels in her attic after T days will be given by the formula ... The number of squirrels in her attic after T days. Hey, I used T the other day for our warthog problem, so I'm in alignment with Taalman's notation. After T days will be given by the formula S of t equals 12 plus 5.5 t divided by 3 plus 0.25 t. Okay, A, verify that there are 4... Is the iPad still up on screen? Is everything still working? Yes. Verify that there are 4 squirrels in Linda's attic at time t equals 0. Okay, I'll do these solutions in line. Okay, so what we do is we plug in, quote unquote, the value 0. So we evaluate this function at 0. 12 plus 5.5 times 0 over 3 plus 0.25 times 0 is 12 over 3, which is 4. Done? Determine the number of squirrels. I'm just going to say number of squirrels as number in Linda's attic after 30 days, 60 days, and 1 year. Okay, so of course the math book writes out some of these things a little bit more. So what we're going to do is evaluate S at 30, S at 60, and S at 365. Hey, Jeffrey, how's it going, man? Good to see you. How are you? All right, so now we have 12 plus 5.5 times 30 over 3 plus a quarter of 30. 5.5 times 60 over 3 plus a quarter of 60. And finally, 12 plus 5.5 times 365 over 3 plus a quarter of 365. So we're just going to evaluate those. Let's try to be smart and do these mentally. This is good mental math practice. So what is 5.5 times 30? I see that as 150 plus 15. 150. So 165 plus 12 is 177. So how did I get that? 5 times 30 is 150. Half of 30 is 15. So I added those two pieces together to get 165. And then I added 165 and 12. Okay, and then the denominator. What is a quarter of 30? A quarter of 30 is the same as dividing by 2 and then dividing by 2 again. So what is half of 15? Half of 15 is 7.5. So the denominator is going to be 10.5. Which is the same as 177 over 21 over 2, which is the same as, so if we divide by a fraction, what is doubling 177? Doubling 177 is 340 plus 14, 354 over 21. Let's see, did we, both of those are divisible by 3, if we're just having fun with it, right? Both of those are divisible by 3. How do I know 354 is divisible by 3? 3 plus 5 plus 4 is divisible by 3. 5 plus 4 is 9, so I can quickly see that 3 divides that. 3 divides a number if and only if 3 divides the sum of the digits. So this is, at this point, this is just for fun because the rest of this problem is kind of boring to me. Let's get some mental math practice. What is 54 divided by 3? I think that's 17. Oh, wait, no. 18. Because, well, I can see 3 times 10 is 30, so that's pretty close to 54. How much is remaining? 3 times what? So how far apart are 30 and 54? They are 24 apart. And then here, if we add those, so I know 3 times 8 is 24. So adding those together, we have 18. 18 divided by 7 is, I think, going to be our answer. And if we ask ChatGPT to check our mental math, did we get it right? 12, because I'm very confident about the first line, and then now I just want to see, did we do our mental practice correctly? All right, so if I just plug this into the calculator directly, I got 16.86. If I do 18 divided by 7, no, well, let's see, what happens? 18 divided by 7. Nope, I did it wrong. Oh, no. Did I type the original thing in right? All right, 18 divided by 7 is totally different. And I should have seen that more quickly. 5.5 times 30 divided by 3 plus 0.25 times 30. Yeah, okay, we did it wrong. Where did we do our math wrong? 12 plus 5.5 times 30 is 177. 3 plus 0.25 times 30 is 10 and a half. 10 and a half, I feel good, is the same as 21 and a half. Yeah. 177 divided by 10 and a half is still the right answer. 177 divided by 21 divided by 2 is still the right answer. Oh, shoot. Okay. All right, whoops. I missed 354. I saw 354. Yeah, I knew I was going to make a mistake here. I saw that that's 100 plus, 300. Yeah, 300 plus 54. 3 times 100 plus, we found it, 3 times 18. Really, I saw 3 times 100 plus 3 times 10 plus 3 times 8. So 118. Yeah. 118 over 7 is the right answer. So I think either of these would be a correct answer, and I like 118 over 7 a little bit more. It's actually the exact number. Of course, we can't have 0.86. We can't have a fraction of a squirrel. So maybe an even better answer would be 17. Or 17 or 16. Maybe that's like even the more correct technical answer. Like probably 17, but maybe 16. right? Okay, anyways, we're getting off track. Let's do the next part. This time I'm not going to bother with the mental math. It's fun, but let's just move on. Let's ask ChatGPT. 3 plus 0.25 times 60. I got 19 in this one. And then 21.43. Okay, so there's our modeling problem. We found the number of squirrels after a certain number of days, 30, 60, and 365. And so we saw that in this problem, 4 to about 17 to about 19 to about 21, right? Even though the number of days was 0, 30, 60, and 365. So we can see how the population is slowing down. The population growth grew really quickly from 4 to 17, and then it grew more slowly from 17 to 19, and then even more slowly because that was only 30 days, but now here was 305 days. It only grew plus 3. Or, wait, sorry, plus, like about plus 2. Right? So I think that that's the point of this problem, that we should be seeing how this population is slowing down and approaching a limit. So back to thinking, like, let's use our brains actively. We are in a limit section. We're not just talking about functions and evaluating functions. Like, why is Taalman asking us this question? How does this relate to a limit? And I bet that'll be in the next part, if we read it. Okay. All right. Approximate S. Okay, the limit as t tends to infinity, s of t, with a table of values. What does this limit mean in real world terms? Good question. Okay, let's solve this one, I don't know, in yellow? Why not? Okay, so if we are going to do this, we're going to burn a lot of energy. We're really going to run ChatGPT into the ground. We might have to ask, we might have to use ON, or O1. Yeah, I might have to switch over to O1 if we're going to compute a lot. And unfortunately, that's going to burn a lot of energy. Oh well, it's worth it. Let's find out how many squirrels there are. How do we want to do this? We could do... We've already found these values after 0, 30, 60, 365. Maybe let's just keep going. You know what? Let's be lazy. Doesn't matter how many years this is. Let's find that number of years, that number of days, that number of days, that number of days. And let's ask ChatGPT. Sorry, environment. Sorry. Okay. This one was about 21. This one was about 17. This one is exactly 4, After 30, there were about, oh wait, no. This one was 19. This one was about 17. Okay. Yeah, all right, so at 1,000 days, we've got 21.779. 21.79, which is about equal to 22. 21.89. And then 21.95, which is again about 22. So our guess is our approximation is going to be that the limit as t tends to infinity of s of t, it looks to me like it's going to be 22, because these numbers keep approaching 22. I just plugged in an extra 0 into that, so now we have 40,000, and we got 21.99995. Again, that's really close to 22. So the attic can support at most 22 squirrels. For example, due to limited food. Maybe because there's not enough food in this attic for more than 22. So anytime that there are more than 22, some of these poor squirrels starve or something like that. That's my thought. Okay, so there we go. We did 75. We did an application problem. Now we have a proof. But I'm going to be right back really quickly, and then we'll do this proof in just a second. All right, y'all, we are back. Let's do a proof. Let's do a proof. This is gonna be fun. Number 78. Oh wait, oh no, there was another question about these squirrels, these damn squirrels that are overrunning the attic. Part D does say, Part D, graph S of t with a graphing utility and use the graph to verify your answer in part D. Okay, I don't feel like it. To be honest with y'all, I don't feel like it. Times 0, like what would it be? It's going to look something like this function only exists. Prove it. Proof it? Yeah, we'll get to the proof in a second. The proof is way more interesting. We've got 22 squirrels at max. This function is going to look something like this. If we asked, I don't even know if ChatGPT can graph equations yet. So how can I possibly ask? Like, ChatGPT can't do this yet, so I think we're just going to have to skip that problem. But I can imagine that it's going to look something like that. Number 78. So we are now doing a way more interesting thing, a proof. Good to see you, G guy. How are you? The quantity 1 over k squared is in this interval for all k greater than 100. What does this have to do with the limit of the sequence 1 over k squared as k tends to infinity? Cool. So this is an example of how I think Taalman's book is really beautiful, because here she's hinting at the idea of how you can find limits of sequences, not just functions. And we saw yesterday that in other books you define the limit of a function based on the limit of sequences. So she just kind of sneaks it in there in the exercises, which is great. So, because I think that this is the first that she mentions, like, the limit of a sequence. All right, prove that for all k greater than 100, the value 1 over k squared is in this interval. So let's say, note let's say that the interval we want to talk about is a and 0.0001. That is the same as 10. We move the decimal 1, 2, 3, 4 places to the left. All right, so the interval is from 0 to 1 over 1,000, right? Let k be greater than 100. Then k squared is going to be, anytime you multiply a number bigger than 1, if you square a number bigger than 1, you get a number even bigger than k. Like k squared is going to be greater than 100 squared. So k squared is greater than 1, 2, 3, 4 zeros. I can see that because you double the number of zeros. Then, when divided by k squared, as you divide by a bigger number, then the inequality flips. 1 over k squared is going to be less than 1 over 1, 2, 3, 4. How do you see that? How do you see that the inequality flips other than just knowing that that is how the inequality works? Because I always show people that if A is greater than B, then you can subtract A from both sides, right? And that's why, like, when you multiply, quote unquote, a inequality by -1, like, you can add and subtract, and then that's why when you multiply by -1, the inequality flips. How do you see that for multiplying by the inverse? I don't know, but I'm going to take that as a given. And that's what we wanted to prove. So 1 over k squared is less than 10,000. Oh, wait. This 10 to the -4 is... I'm blanking so much right now. 10 to the 4th is, 10 to the 4th is 10,000. There should be 4 zeros. So now, 1 over k squared is going to be less than 1 over 10,000. And k squared is greater than 0. So 1 over k squared is also going to be greater than 0. Thus, 1 over k squared is in the interval 0 to 1 over 10,000, which is the same as the interval that they asked about. And then the next part, the limit of the sequence 1 over k squared as k tends to infinity is 0. Because for any epsilon greater than 0, we can find a k such that 0 less than 1 over k squared is less than epsilon. I.e., if epsilon is a very small number, 0.0001, k equals we can take the 100th element of this sequence. So 1 over 100 squared, 1 over 101 squared. If we think back to our Cauchy sequences and whatnot, the sequence definition of a limit here, everything less than that nth term, 100, does not satisfy the precision of epsilon that we wanted, but then forever after, like every term in the sequence after, is going to be within that approximation tolerance that we're looking for, epsilon being 0.0001. So that's basically the, there's an example or a proof about sequences and limits of sequences. It's a little weird that this question does ask about how do you know what the limit of a sequence is without the section talking about a limit of a sequence. But it's cool. I mean, it just kind of like intuitively teaches you this idea of like, oh, what would that mean? What would that mean for a limit of a sequence if there is a concept of a limit of a sequence? So, neat. And then one final question is actually going to be exactly what we're talking about right now, what I'm saying. Convergence and divergence of sequences. It says in this thinking forward. So thinking forward means like in a future section of this book, we're going to talk about this concept. If a sequence A1, A2, ... AK ... approaches a real number limit as K grows without bound, then we say that A of K, or the sequence AK, converges. So just like we saw yesterday, we can define limits of a sequence, and just like this problem also just, it bothers me a little bit that Taalman had an exercise about limit of a sequence before defining the limit of a sequence, but that's okay. That's good. That's a good thing. It builds intuition in math, and like in math, you have a thing that you do for a while. I don't know where I'm going with that. All right, so we have convergence of a sequence, and then blah, blah, blah. There's a little bit more, and we say that the sequence diverges if there is no limit. And then it says, write out enough terms to make an educated guess about whether it converges or diverges. So this sequence is going to be the sequence 1/4, 1/16, right? 1/4, 1/16. What is 4 cubed? 164. Okay, I feel very confident that this is going to tend to 0. 5/4 to the k. The sequence is going to be 5/4, 25/16, 125/64. And that I feel very good that that's going to go to infinity, but let's try to get some numbers so that we can really see that each of these is getting bigger, right? Like we've got 1.25, 25/10, well, I know that that's 2.5, 125, 125/64. What the hell? Oh, no. Oh, that's 25/16. Oops. 25/16. I'm a mathematician. 25/16 is 1.56. 125/64 is 1.95. So this gave us a point. We added an extra 0.31. Here we added an extra point, 39. So the fact that this next term grew even more than the prior term, I bet that this next one is going to grow by like 0.4 something, maybe 0.45, and then 0.5, maybe 0.55, something or other, which means that each time it's growing even bigger than before. This is not going to approach like any limit number. Okay, here the sequence is going to be maybe 1/3 if k is 1. If k is 2, then we have 2/4. If k is 3, we have 3/5. If k is 4, then we have 4/6. If we reduced these numbers, that one's 1/2, and this one is 2/3. But ... what if k was 100? Then we have 100/102. If k was 1,000, we've got 1,000/1,002. ... So there's a bunch of terms in the sequence. I feel very good that this is going to, the limit is going to tend to 1, because these two numbers, the numerator and the denominator, are getting closer and closer to one another relative to each other. And then here is going to be very similar. We've got 2. We have 3/2, 4/3, 5/4, ... 1,001/1,000, on and on. I feel very good that that is also going to tend to 1. All of these converge. So even though the numerator is greater than the denominator of this sequence, it still converges. All of these get very close to 1 within some epsilon tolerance level. Convergence and divergence of series. This one says calculate partial sums of this series. So now we are thinking of the sequence where each term is a sum of 1/n² squared. So we have from n equals 1 to k. So how many terms? Like the first term in this sequence is just going to be 1, and then 1 plus 1/4, and then 1 plus 1/4 plus 1/9, and then 1 plus 1/4 plus 1/9 plus 1/16. We could ask ChatGPT, how many partial sums are we going to need to convince ourselves that this is going to converge? So here I've written out some partial terms. 1, 5/4. Let's see. Let's just get decimals. We're not going to be that fancy. Let's just do decimals. 1.36. 1.42. The next term is going to be 1.46. And then just for fun, 1/36 is going to be the next one. 1.49. So this, like, just notice that each time that we take another extra term, the difference is getting smaller. These two differed by 0.04. These two differed by 0.03. These two differed by 0.06. So I think that we can see that this is going to converge to something. Maybe it converges to about 1.5 something. And now let's see that this one diverges. 1, 1 plus 1/2, 1 plus 1/2 plus 1/3, 1 plus 1/2 plus 1/3 plus 1/4, on and on. So this is going to be 1, 1.5, 1.83, and then 1/2. I wish you all could see me talking to ChatGPT. 1/3. I'm not actually, obviously, you all know that, right? You've picked up on that. I'm not actually talking to ChatGPT. I'm asking a calculator. Sorry to ruin the illusion. 2.28. 2.45. Okay, so how do we feel? These two differed by 0.5. These two differed by I don't know. I don't think that that's going to be enough. This argument is not going to be enough to see that that this is. I don't know. It doesn't seem to be tending to a single number like nearly as quickly as the other. So if we just keep writing out terms to convince ourselves, two. I think that this problem said a calculator is useful here, and I agree. A calculator is very useful here. 2.83. So we are still not reaching anything interesting. 2.93. So how many terms do we need? Like, probably pulling out Excel would be the best way to really be confident on this. 3.02. I don't know. How do we know that we just haven't taken enough terms yet? But by 1, 2, 3, 4, 5, 6, by the sixth term, the growth really seemed to be slowing down, and we're getting very close to 1.5. Whereas on this one, we've taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms, and still growing. ... So that's a really cool case, because now we're talking about this series diverges, whereas this series 1 over n squared converges. So it's not enough to say, that the sequence in a series, that if the sequence converges, that the series converges. So that's fascinating, because 1 over n tends to 0, but the series 1 over n actually grows without bound. So that's really cool. That's a really cool thinking forward problem. I really love this book so far. So this is in the first introduction to limits, and Taalman is already talking about series. That's so freaking cool, if you ask me. If you actually do these like thinking forward problems. All right. Hey, Wing. I'm just going to call you Wing. Keep up the good math streams. Thanks, man. Thanks, person. I'm glad that you're enjoying them. I'm having a lot of fun. It's a great positive pressure for me to just do math instead of scrolling TikTok or whatever. So this is super fun. I'm glad that you enjoy it. Hit the like and subscribe. Leave a comment, all of that good stuff. Share it with your friends. Share it with your teachers. I'd love to build a cool community here of people who are fellow math hobbyists or students. And I'm mixing and matching, doing a wide variety of subjects and difficulty levels. So stay tuned. Let me know what kind of math you would like to see. All of that good stuff. Thank you all. Have a wonderful day. Bye.